Okay, I say we need a new atomic model, no question whatsoever, so we need a new periodic table. Now why? These are the two smallest particles anybody has ever seen. They call that a muon neutrino and an electron neutrino. And this is Fermilab. And they also say at Fermilab that the Standard Model is the most successful theory ever. These are those two particles they're talking about. Right? And they make gluons and photons, and then they throw in all these other things because they're just parts of the debris that they see, and they think they're fundamental particles. They are not. So the Standard Model is not successful at all. It doesn't account for gravity. It doesn't account for dark matter. It doesn't account for a lot of things. Isotopes. You can't make isotopes work with this. It's absolute nonsense, really. But here's another thing they say at Fermilab, same thing. Empty space isn't empty. Absolutely it isn't empty. Does that look empty to you? Does that space look empty to you? Let me show you a space that you can see the fields and everything. And this is just taken right here from Earth. You can see all the fields everywhere. All right, but I'm just basically going to read through it. And then I am going to explain it a little later. The anatomy of a proton. All right, dipole electron flood theory is a new atomic model, changes the nucleus from a completely positive into a dipole made of tiny dipoles. Dipoles just means positive and a negative. They're called Dirac neutrinos instead of a large positive only core and a bunch of little electrons. Protons and neutrons are made of dipoles just as everything is. In certain stable quantities we now call atoms in various sizes. These are the atoms. Now, and they can become stable at certain sizes, but a hydrogen proton is 1,823 particles. It's stable at that point, but you get smaller than that and they just fall apart. And then you get bigger, and only certain areas, like between here at 1,825 or so, by the time you only get to helium, which is the next stable one, you're up to like 7,000 and something of these little particles. So it gets big quick, and it allows for biological activity and all that stuff. But the anatomy of a proton is not one big positive that they can smash into quarks and all these little things. No, it's all dipoles in a ball. All right, so when they smash them, they get a whole batch of stuff, but it's just all debris. Whoops. There goes the dark matter. Dark matter sits in the center of everything. That's the dark matter right there. Now, particles are everything there is made of the white particle and the black particle attached together. As these, every ball of these is these two together. It's a magnet. It's a bar magnet, but it's in a ball shape. And they pop together, and then they all add together until you get to 1823, and that is a proton. A neutron is 1824. It has a neutral number. So you got muons and you got electron neutrinos. And the difference between the Standard Model and this model is that the nucleus is made up of all of these, but there's 1,823 of them. It's not made up of a bunch of little particles that are just all kinds of different things. It's made up of all of these in different states. When they smash them, sometimes they get pieces this big, sometimes they get pieces that big, sometimes they get pieces that big, sometimes they're in a circle. They're all kinds of crazy things that they see. And they say, oh, it's a particle zoo. No, it isn't, just pieces formed in different ways. All right, now here's what's going to change. These are changes in science as a totality. Dipole electron flood theory, what changes in science? With the mounting evidence leading to the realization that the universe and everything in it is made up of these dipole particles, the changes will need to take place in academic textbooks of all different sciences. You can't start with a wrong model and everything grows from it is right. No, you have to start from the right model and then everything grow from it. So what about chemistry? Periodic table has to change. That's not a 1. That's a 1825 or something. And it's all going to be totally different. But it will account for everything. As we can see, the growing number of electrons, you know, electron neutrinos, surrounding that dark core, it'll start to make sense on how molecules and isotopes particularly work, and half-lives. Because a half-life just means you got an atom that doesn't have quite enough of the right particles. So some of these are missing. All right, and it'll only stay stable like that for so long until it attracts enough, until they fill in all the missing spots. And then it becomes stable. Same thing if it has too many of these particles. It has to kick them out. That's what isotopes are. So we got chemistry problems we got to work on. Space, and space is totally wrong as they have it now. Everything in space has fields, and there's particles, and so light coming through it is going to slow down, absolutely no question. So the redshift, totally wrong. We have literally no idea how far away things are from us, because everything is based on the speed of light never changing. I show that's just not true. Speed of light is very variable. And the more fields and debris you have in front of it, the slower it's going to come. It's going to just keep on boom, 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 boom. It's just going to slow down. All right, we put it through a Venturi to speed it up. So we know we can speed it up. And that Einstein says no, is impossible. We know we can slow it down. Everybody knows you can slow light down. So Einstein was just wrong, and nobody can speak against it. That's why having an unrestricted ability to post something like this is just, that's unheard of. I'm hoping that's the case. You know, I just want you to know, this is really a red letter day here for me. Because I got honestly, I got jaded, because every time I would submit anything, it would just be rejected instantaneously. I would just waste all my time. So I just went to YouTube and just kept posting and posting and posting. And to be offered a full waiver to submit my work, that's seventh heaven for me. So let's see if that actually happens, and what is the result. There's 260 million people are supposed to be able to see this. We'll see. You see this? This is an artist's rendition by CERN or somebody. And they're looking for these gravity fields. Well, if they're looking, we found them already. Here they are right there. This was just taken with a cell phone. And these are the energy fields that the phone was able to pick up. This was Dylan Carpenter took this. He's out of New Zealand. It's Rod Warren's nephew. Rod did basically almost all the other stuff. Well, not 100%, but a lot of it. Well, almost all of it. And this was what Rod's work was right here. You saw those two particles from Fermilab. Here it is right here. That's coming through the Venturi. And looking, it's a photon. There's no question it's a photon. It's two of those W and Z or whatever they are particles. Here's the deal. Where is it? Hold on a second. All right, this is actually very, very simple. These are the only two particles that exist. The only two particles that exist. One of them is black and one of them is white. That's it. They can be separated on the subatomic realm. But once they become into atoms, they don't separate. The only way you can separate them is to smash that atom to bits. Now, the black and the white together is what's called a gluon. Right there, a gluon. These two glue on to each other, and they are glued on. They understand this to some degree. Now, two gluons back to back make a photon. So you have one this way and one this way, but together, as I will show you, make a photon. That's it. All the rest of the stuff is just different pieces of this in debris when they smash them. And they see all these things, and they see them over and over and over again, and they think they're particles. They're not. Here's what they do. They take two huge particles here, a neutron, or let's say this is the proton, the dark one, and this is the neutron. The proton has just one less dipole than the neutron. The neutron has an even number. The proton has one less, so it's charged. It wants to take one more on to become neutral or give one up and bond with something. But what they're doing is they come around, 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 bam, they hit these things together. And they only hit a few of them here and there. And when they do, they just get a bunch of debris. It's just because they're actually sending these things around and around and around, and bam, they hit together. And then chunks go flying like this, everywhere. Just everything goes everywhere. Just a big ball of mess. Well, we started with light. This is actually what a photon is. As I'll show you, we started with that. So we didn't have to see all this mess. And we were able to use CMOS because CMOS is designed to see light. And this is nothing more than light. These are the smallest particles. So they're not like pieces like the X, like this, a big chunk here, smashing into CMOS and destroying it. CERN just upgraded to use CMOS so they could see better and not interfere. Before, well, here, let me just show you something. Where is... listen to this. If you magnify the extended particle, this one, the black one, it just gets bigger. It's just because it's a piece of matter. It gets bigger and it gets smaller as you magnify it. But listen to this. A point-like particle, which is this one, will not change in size, but the more closely you look at it, the stronger the field surrounding it becomes. It gets puffier and puffier and puffier the more you look at it. Well, why? Why would that happen? Just because I point my eyes towards it, it gets puffier? No. It's because you're putting energy into it to see it. That's what they do. When they say you look at it through some kind of a device that actually adds energy and puffs it up. As simple as that. It's just like blowing up a balloon because you're pumping the energy in. This one won't... dark matter, which is this. This is dark matter. It doesn't absorb. So when you send energy into it, it doesn't do anything. You just see it like what it is. So it doesn't change in size. It doesn't reflect. It doesn't emit. It doesn't do any of those things. It's dark matter. So we never see it. And the only reason we never see it is because it's inside the center of atoms. And that's atoms are the smallest things we can see. So there's where dark matter sits, just like that. That's it. Everything you look at has dark matter inside of every single atom because they're all made of dipoles. But in the atomic world, all the black collects in the center. All right, it's this. This is what happens with a proton. All the dark goes to the center, and a huge cloud of electrons surrounds it with the same number of electron particles as there is dark particles. I think. It might even be a little bit different. I don't know. There might be more dark particles than there is white particles because it still wants to attract more. And then they keep out at a distance. It's called a quantum distance. They can't quite get in because there's too much pushing them back out. It says, I'm stable, I'm stable, I'm stable, stay away from me. It says, no, I want to get back in there. Well, why would it want to get it back in? Maybe there's more black. And it wants to attach. But because it's stable, it says, no, you stay out. All right, but we need a new periodic table. There's no question about it, absolutely none. Okay, this little video just is in support of showing you the dipole electron flood theory. Now, again, this is my model of the proton. All the dark part goes to the center, and it's made out of all dipoles. When you get down into the subatomic range, you can separate the positive from the negative. You cannot do that in atoms. You pull them apart, bar magnets, you just end up with 2 bar magnets. You break those, you got 4, you got 8, you got 16. They're never going to not be bar magnets. When you get down into the subatomic range, the white separates from the black, and that's the 2 particles. These are the 2 particles that make everything up. That normally they would consider a positive particle, and this normally would be considered a negative particle. And the 2 of them glue together. They actually call them gluons. All right, the 2 particles glue together. When these 2 made up with another 2, they become photons. As they become larger, at 1823 or so, they become protons. 1824 becomes neutrons. So basically, to visualize it, it would be like this. That's a proton, that's a neutron. When they smash them together, they get all kinds of bits and pieces. Well, they actually consist of this particle right here, which is the proton or the neutron, doesn't matter. They have 1823 for the proton, 1824 for the neutron. Deep inside the center is where the dark matter is, because it congeals into the center, as I showed before. Now, there's going to be some changes to science and chemistry, space. A lot of things change. The redshift is not realistic. Light slows down. It doesn't shift because it's being pulled away. Space, time, distances, we got some work to do in those areas. All right? And this is the new atomic model. All right, before we get started, let me explain. This theory goes back to a very long time ago, 50 years ago. I had that there's only two types of particles. There's dipole-dipole interactions. Some of them are polar molecules, some of them are non-polar molecules. And this was my statement. The Rutherford's atom is wrong, which the Bohr model is based on. You can't base your model on the wrong premise. I say that the transfer of energy is from light to atomic vapor. Light is really the particles that make up everything, as I will show you shortly. This is what I say a proton is, which is a bunch of dark matter, literally dark matter, that is in the core surrounded by tons of electron particles, which are the glowy particles that we see. But the dark matter's deep inside, so it's never been seen before. The only time you ever see that is with the particle colliders, and then they really don't know what they're seeing because they just have a bunch of debris. We use light, so we got off a little easier. All right, I'm just going to briefly go through these things. This is the Dirac neutrino, which has got the white and the black particle, just exactly what I showed you over here. These are Dirac neutrinos. Now, what we did was we took light, which is this here, from a red laser, and now it's just starting to accelerate. It's pushing through all the other fields that are in the air, because every single particle, every single gas, every single bit of heat has a field around it. So we have to push our field, which is this big field, through all of their fields. The particle is down in here. This particle is just a tiny little thing way down in here. There's almost nothing there. But the field surrounding it is what's got to get through the air. So it creates a havoc around it. So as that goes through the air forward, we accelerated it because of a venturi. A venturi is nothing more than like the nozzle on a hose. It comes in at a certain speed, it goes out much faster, and there it is right there. And a venturi is what atomizes things. Well, we're atomizing atoms. We're turning into subatomic particles, and they're subatomic here. Here, they're actually light, which is actually subatomic too. But you can see the wave produced by the particle. Now the particle is being pulled directly out of the wave, and it's accelerating. There's no real question about that. This is a subatomic nuclear explosion. The white particles are just exploding like a bomb, and the black can't get through. The black stays here, and black pulls back in over here. So there's got to be some black just laying around waiting to catch on to because I don't think this black jumped over ahead of it. Let's look at it real careful. All right, so again, this is the light just starting to accelerate. This is the light really accelerating. This is when it hit the venturi. Here's what it did. It took the muon neutrino, electron neutrino, which is the Dirac, and it split it. It kept the black off to here, and it let the white come through. There's no other way to say it. It's fission and fusion. And in between here, this is raw electron showers. Electron showers have absolutely incredible amounts of energy. And they know this. We should be able to get free energy out of that. All right, just to make this as clear as I can possibly make it, we took the light, we accelerated it, the particle divided. The particle on its way to the venturi looks like this. Now what you're seeing here is neutrinos. These are all neutrinos. These are photons. Now the reason these have fully fledged photons are because they are stacking up on themselves because they can't get through that Venturi. They're being pushed back. So these think they actually literally hit a wall, so they start glowing like a regular photon would. During the air, as they move through the air, they just don't have enough energy to be real fully fledged photons. But once they bounce off a wall, that's when you see. That's when you see the bounce back is what you're seeing here. But this already thinks it hit a wall because of the reverse of all of those particles. And this is when they reverse. All right, they come back this way, so now these particles here start glowing like crazy. Now the green and the black, the blue and the red, they're all the same. These are the same particles. All right, so they're the black and white Dirac neutrinos. Back to back makes a photon. A single Dirac neutrino is literally an electron. That's what an electron is. We never knew that. We always thought the electron was that glowy part, and that's all there was. No, it's attached to dark matter. Isn't that funny? Dark matter is right in front of our face all day long. Now, when they do at CERN and Fermilab and all the rest, they smash these big particles like this. They get all of this debris, and they say, wow, these are all special particles. They're not. All they are is pieces of these. Some are big pieces like the X's. Some are little pieces like this, like just the glowy parts. Some of them are photons. But they're just all made of these dipoles. So there's not all of these particles, there's just two little particles. Okay, let's wrap it up with this. If anybody has any questions about this, I'm more than happy to answer them. Now that's the light, it's starting to accelerate. This is full acceleration mode, where the particle is being shown, coming through the Venturi. This is coming at us through the Venturi. These white particles reconnect with the black particles and forms Higgs fields. These are Higgs. All right, so that's the new atomic model dipole electron flood theory. Okay, my excellent friends, if you have any geek whatsoever, you know about the periodic table of elements, atomic chart, basically. It starts off with hydrogen being the smallest element that is stable. And then it goes to helium and all the way up to get up to these very, very heavy elements, uranium and so forth, which are just gigantic balls of matter. This is the smallest, and it's a gas. It's so light, it just doesn't have enough particles in it to be attracted to the Earth. So it floats, it goes up instead of down. Virtually everything else goes down. Helium goes up too. But virtually everything else comes down to the ground because it has enough mass. And what is mass made out of? Mass is made out of dipoles, just like this. It's not made out of protons like this. All right, one proton is made out of all of these little particles. And all of these little particles are tiny little bar magnets. That's all they are. They're little dipoles, two poles, a positive and a negative. Think of it that way. And they ball together in certain quantities. And hydrogen is to a physicist right now, they would say that's one big proton and one tiny little electron, which is like 2,000 times smaller than the proton itself. It's just not correct. What it is instead of being this one big ball, it's this one big ball made of tiny little bar magnet dipoles. Now I have a completely new periodic table, and it's based on dipole electron flood theory, which says that the only things that exist in matter is the dipoles, and they just get bigger and bigger and bigger and bigger and bigger, and they stabilize at certain quantities, and that is what's called resonance. Now, it's a little foggy to me, because they just keep getting bigger and bigger and bigger and bigger and bigger until they get extremely unstable up at uranium, plutonium, up in those areas where there's just too many particles. They just can't stay together. Simple as that. But we have to change the periodic table of elements. So I did a thing the other day about Joe Rogan and Terrence Howard, and here it is right here. Terrence Howard went on Joe Rogan, spoke about his new periodic table, gravity being fake, and then he went on, he went on a bunch of nonsense about 1 times 1 equals 2. Well, all of that theoretical calculations based on pre-assumed assumptions of this and that with numbers, none of that stuff works. It's just nonsense. You have to look at the material evidence, not some theoretical, law or a foundation of this, or like Einstein's law. You can't accelerate light. That's just insane. You can accelerate it, you can decelerate it, and when the universe is not pulling away from us and stretching the light to make it look red. The light is just coming slower and slower and slower. Instead of being blue, it's coming down to the red section because the wavelengths are getting longer and longer and longer as it slows down. It's not just being pulled away. So virtually everything that we know about right now is based on the standard model, and the standard model is not correct. And I will show you what the new model is, and it's based on a new periodic table. And that's what we need, is a new periodic table. Now, this was just a bunch of nonsense that he was talking about, really. And I don't know about his periodic table, but I wanted to join in and say, yes, we do need a new periodic table. 100% true. What he was showing was based on some kind of, like, artwork, basically, is what I took away from it. Because he makes all these patterns and these twisted little graphs of all kinds of numerical things, and seems to think that points to some new evidence. And it might, I don't know. I didn't follow it. But I didn't really pay that much attention to it either, because once he said 1 times 1 equals 2, well, I have a hard time following that logic. So anyway, let's get started about the new periodic table and why we need it and what electron flood theory is. This is what the proton looks like, not like this. Proton is like this. It has dipoles, not just one big positive. So I'm just going to show it to you again. I've shown it over and over and over, but I need to get somewhere to pay attention to it, to peer review me. I asked Tyson, whatever his name, Neil deGrasse Tyson, and I need a celebrity. I need somebody that has some exposure to the world. I am been put in a box long ago, and I just barely am seeing outside of that box in the last couple of years. But it just doesn't, I just can't open the lid all the way. So you're going to have to help me. You guys are going to have to help me. I can't do this myself. I just cannot do this. I am so restricted in most every area. I think my emails go out and they're considered suspicious. Watch out for this. Because I get them from other people too. It has a big yellow tag on it, said, may be safe or something like that. It makes it really sound like you're a nutcase if you open up this. So, but we're starting to get there. And the dipole electron flood theory is just one piece of the puzzle. All of the rest is about the mud fossils. And our history's wrong. The chemistry's wrong. The subatomic realm is wrong. Biology is wrong. I mean, everything's wrong because they don't understand dipole electron flood theory. If you don't understand what everything's made of, how are you going to understand the end result? You can't. You can't look through space and say light never slows down. Of course it slows down. Obviously it slows down. We know light can slow down when it passes through other media. There's no question about that. And they say that space is a vacuum. They know now that that's not true. And it's been known forever. And actually right here, there's a quantum foam. Empty space isn't empty. This is over 10 years ago. All right, but they still can't get their heads around the standard model's not right. We found these particles. I'm going to show you all this one more time. Well, I'm going to show it forever until it finally gets peer reviewed. That's all I want. I just want somebody to peer review it. That's all. I have so much evidence to support my claims, you'd have to be crazy not to understand it. These are the Dirac neutrinos, the smallest particles they've ever seen. Matter and antimatter, they say. Well, it's actually the electron neutrino and the muon neutrino. The Majorna neutrinos are just are these, but not quite up to that strength yet. And I can show that in the light experiments. This is light coming through the air, and it's sort of interacting with these other particles. Not a whole lot. It's starting to accelerate. All right, now here's full acceleration. Like a rocket ship. Let me see. I got another one showing it pulling itself out of the wave. Hold on. All right, here it is. This is the wave coming through. And the reason there's a wave is because there's a ball of magnetic energy surrounding a tiny little particle. And there's the particle right there. Now it's accelerating like a rocket ship. And why? Because there's a venturi here. Just look it up. Venturis make things accelerate. It's just like the nozzle on your hose. You turn on the water, it comes out at a certain speed, not a whole lot fast. But when you put that nozzle on there and you tweak it down, the water gets crazy, just like this. It's acceleration, and it pulls it right out of its own magnetic wave. And right here, you can see the photons. And here they explode. They actually divide. And that's why I can tell you that, and this is, a lot is based on frequencies of light. The same particle here is green, blue, red. And they understand these different colors. Now, because they see these things. This is fission, it's fusion. That's acceleration. This is impossible to not understand this. It's really ridiculously simple. There it is. There it is, fully accelerating. Here it is when it hits the venturi. The black actually separates from the white and lets the white shower through. Precisely what they want to see. This is exactly what they want to see. The muon neutrinos turn into just sterile muons, the black ones. They're no longer attached as the Diracs. And the electron neutrino goes off into a shower. This is what they wanted this is what they want to be able to do. We did it. And then the black comes back. We need a new periodic table. All right? These particles make up matter. Light is atomic vapor. Now, hold your mind for a second. What is vapor? What's vapor? It's basically like diffused molecules from something that was solid. Well, we're taking these light particles and turning them into a solid. That's what happens. Light turns into solid things. Because these are the only two things that exist. These two particles. Right? They come out of the sun, they hit plants, the plants turn into matter. And I did a calculation how fast the Earth should be growing based on how much radiation is hitting the Earth. And they say, oh, no, it's just going to go back off into space. No, it doesn't go back off into space. Once it gets into our atmosphere, into our Earth, it becomes a particle that stays down here because the outside particles, the ionosphere, is nothing but electrons. The dark matter stays down below the electrons. The electrons surround the atmosphere. They're called the ionosphere. Ions are the electrons. Ions. All right? And the dark matter is below. That's the heavy stuff. It doesn't go back out to space. They just don't understand space is nothing but loaded with particles. As we spin through it, it scrubs our atmosphere. You just don't even understand that. And you can't understand anything until you start to understand dipole electron flood theory. They don't understand why the outside of the atmosphere. Hold on one second. All right, this is what's happening in galaxies. They spin around a center, which they call a black hole, which, yes, it is. It's congealing around a gravity source, and the dark matter is the black hole, and it sucks all particles into it. Now, we're going to be on one of these arms, spinning like this through space. What does it look like if we got right down to our solar system inside of here? Here's what it looks like right here. That's our sun. And it's going through the Milky Way. Everybody has to go the same way. We're spinning around behind it, trying to catch up to it, because its mass is pulling our mass towards it. It's just mass to mass is attraction. It's gravity. And this just has a lot more dark matter, which attracts our mass towards it, and we're spinning behind it, trying to catch up to it. Basically, that is our solar system. Now, what does that mean to our weather and so forth? First of all, this is a solar eclipse. This is the moon, and it's over the top of the disk of the sun, so we can see all the radiation. These are not just glowy little light, well, it's light, but it's all particles. Light is nothing but particles, and they are spewing everywhere into the solar system, and we are plowing through that, as I showed you before. So what are we doing? We're plowing through the stuff that's coming off of the sun, and we have to plow through those particles. All right, that's what is light is hitting us. Those particles of light, that's what we're plowing through, and that's what warms up our atmosphere, the side that points towards the sun. All right, so let's get into the practical effect. We know we're spinning around. We know the sun is spewing out all kinds of stuff. Now, at our surface, what does that mean? All the stuff spitting out here is electrons, basically, and particles. We have to scrub through them. We're scrubbing through them. There's no other way. We're scrubbing through them. Now, why are we having such terrible weather? Our gases are expanding like crazy. Every time we burn something, it makes thousands and thousands of times bigger gases than it was when it was solid. And we're burning stuff like crazy. So it's expanding, and as the hotter it gets, the more expansion it gets. Well, guess what? It just doesn't bleed off into space. It's being forced into our Earth, and the Earth is growing with every day the amount of particles that are being captured. Now, on the other side of the Earth that is not facing the sun, some may evaporate out into space. That I'm not sure of. I would love to see an experiment that said, on this side of the Earth, at the ionosphere, what is the temperature? On the other side of the Earth, at the ionosphere, what is the temperature? Is there a variation? Does it go down? If it went down, we'd know that some of it's leaking out. If it stayed basically the same temperature, we'd know that it's still scrubbing, so it's got to go inward. Now, what would that do to the temperatures? Whenever you scrub something, it gets hot. Well, whenever something gets hot, that's a dipole, so the hot is going to create a cold. Does that happen in our atmosphere? Yes, it does. All right, let's talk about why particles don't go back out into space. They're collecting here. This is the ionosphere, ions. Ions means electrons. It's 1,500 degrees Celsius. That's 2,700 and change Fahrenheit. 2,700 degrees out here. Everybody thinks it's real cold. It gets colder out here, yes. Here it's 2,700 degrees. There's nothing but electrons here. And then guess what? Just below that extreme temperature, it's minus 80 degrees Celsius, which is minus 112 Fahrenheit. So you got 2700 above Fahrenheit minus 112. That's 2800 degrees difference, and it's separated by this one layer. That, my friends, is a dipole. And what's going to happen again is you're going to get another zone of heat just below, and then it goes into the Earth, which is the cold. The Earth is a sink. The Earth is ground. All electricity wants to get to the Earth, and this is where the electricity is coming in. And it'll hit you and it'll burn you. If you're standing on the surface of the Earth, it'll actually, you get sunburn. You're getting hit by particles, they're burning you. They're coming through this stuff. Now, most of it's stopping out here. Most of the electrons are getting absorbed out here. All right, this layer is what protects us from all of that stuff burning us. But it doesn't let the electrons go back out to space. They stay here, and that's why it's so hot out there. And the more electrons we put into the air, because heat is nothing more than extra electrons. Heat is, you got to understand this, heat is nothing more than additional electrons. Additional electrons. That's what heat is. If you force electricity into a wire, it'll heat up. It's just going to happen. It's going to heat up because it's just got too many electrons. If you go down to absolute zero, where you don't have any of those extra electrons, you have none. Absolute zero means there's no more electrons. It means absolute zero of extra electrons. You don't have any extra electrons. You put electricity into that, it goes right in there because it wants to go there. All the electrons are missing. They want to be up to where there's some kind of a temperature in there. And as soon as you put that electricity in there, it starts to resist. So you can only superconduct for instantaneous like that. Or else you have to continuously put more and more cold in there so that it stays superconductive. Now they're working with certain types of metals and so forth that appear to be highly conductive. They're not going to be superconductive. Superconductive means there's no resistance. Well, you know, that's a gray area. If I say superconductive the way they say, no resistance, it just go forever. No, that's never going to happen. There's going to be resistance. How much is a matter of, first of all, the temperature. If you can get to absolute zero and you can stay there somehow, it would just go. Yes, I agree with that. Because it wants to just give me all you got. Zip. But as soon as it start packing up in there, they start to resist. So I don't see any way you're ever going to get superconductivity at that level of continuous no resistance. You're going to have some resistance. So they're going to be making strides in certain types of metals that have a lot of extra electrons. If they have a lot of extra electrons, or maybe it goes either way. If they have a lot of extra electrons, maybe they can push easily. If they don't have a lot of extra and they want electrons, maybe they'll suck electrons in. And these are called isotopes. All right, before we go on, I just want you to understand, that's why it's heating up here and we're getting so much turbulence down here, is because we're expanding and blowing up like a balloon. Too much here, too much. So you got hot, you got cold, then you got in our region, which is hot again, and then the Earth is the cold. Everything's a dipole. Hot, cold, hot, cold. Earth is the attractor of everything. Even though we consider Earth to be fairly warm, it's not. It's cold. It wants electrons. And once they're below this layer, they don't leave. They don't leave. They stay being pushed down in here because of our scrub through the solar system as seen right here. We are scrubbing, and as we scrub, it forces it down as seen here. we're scrubbing. As we do, we scrub here, and it pushes these electrons down into our ionosphere. That's why it's 2,700 degrees out here. Now, what about here? What about the sun? How hot is the sun? How hot do you think the sun is? Da, 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 da. How hot? Well, how hot? All right, 10,000 degrees. All right, 10,000 on a surface. That's not that hot. What about out here? How hot do you think it would be out here? It's millions of degrees out here. 10,000 here. They have no explanation for that whatsoever. They say, oh, it's got to do with nuclear fusion. No. It's got to do with scrub. Through all of the stuff that's in space, and everybody's scrubbing through it. Nobody's immune to this. Everybody's scrubbing through this. So we could be fortunate and be moving into a place where there's very little resistance to our movement through it, or we could be moving into a place where there's a lot of resistance, and we're going to probably be bouncing back and forth through that. That's why there's all this intense solar activity, and then there's less solar activity, and then it gets intense, and they get all bubbling up, and it probably hits something. You know, a cloud of particles, basically, some kind of a dense. Like we have what they call these CMEs, the cosmic, I forget the name of them, but they're pulses of particles basically, and they just blow off the sun, and they don't have any reason for that. And I say it probably hit something very dense. A little blob in space that was dense. You could see these are all blobby. These aren't just homogeneous. All right, and anyway, when they get these huge emissions from the sun, for no reason they can come up with, the particles actually hit the wires and everything, and can burn out circuits on the Earth because so many particles are coming down. It's like a Tesla coil coming in and hitting like all the wiring, and if big fields go into the stuff and explode things. That's, hold on a second. All right, it just came to be coronal mass ejections. Well, corona is the outside particles of the sun. All right, that's the corona. And they say coronal mass, which is particles or masses, ejection. Now, those masses of particles come towards Earth, and they hit all the wiring on Earth, which you can induce current into a wire just by passing a bunch of excess electrons, high energy, past it. That's what a motor does. It's just high energy particles passing against wires. And it builds a field, and that field pulses through and destroys circuits and interrupts all kinds of, data and electronic signals and so forth on Earth. That's what a coronal mass ejection is. They have no idea why they happen. I say the sun itself is whacking into something, like something out here that it didn't expect, and bap, it hits it, and you get this ejection. And this is what happens. The sun itself is continuously ejecting because it's continuously scrubbing something. Sometimes it's not a whole lot. Sometimes it might be a whole lot. That's why you get these ejections. And you can see the red spots here. The sun is moving this way. And that's why it's got the field poles going this way. This, of course, is the moon. And you can see it's sloughing off all these particles. All those particles are going out into space somewhere. Space is saturated with all these particles. There's no other way to understand it. And out here, it's millions of degrees. Right here on the edge, it's 10,000. Millions out here. They have no explanation for that whatsoever, because they say space is a vacuum, and therefore light never slows down. Well, that is also complete nonsense. First of all, this is just taken with a cell phone, and these are all the fields of all of the different things that are in space. They all give off fields. Fields, if you got to go through that field, you're going to slow down. It's as simple as that. So when we look off to like a zillion miles away, and oh, that's got to be 500 bazillion miles from here because light travels at exact speed. No, it doesn't. Bip, 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 bip. And there's a cosmic microwave background, which microwaves are very, very small energy waves. They're just basically electrons sitting around that have slowed down until they're just not going hardly anywhere anymore at all. They're just slowing down. They were ejected from the sun or a star or something. But they hit enough of these fields and they just sort of lay around in the background. That's background radiation, cosmic microwave background. I tell you, this would be comical if it wasn't tragic. This is the cosmic microwave background. Listen to this. This cosmic microwave background, CMB, is microwave radiation. It fills all space in the observable universe. It's everywhere. It is a remnant that provides an important source of data on the primordial universe. No, it isn't. It's light that's just slowing down from every source. It's just slowed down. It's very, very slow light. You see this? This is hysterical. It really is. It's hysterical. This cosmic microwave background, landmark evidence of the Big Bang theory for the origin of the universe, the Big Bang cosmology model. During the earliest periods, the universe was filled with an opaque fog of dense, hot plasma or subatomic particles. I can't discount any of that, but I can tell you what right now. All of this cosmic microwave background is just electrons and protons that have just slowed down. They didn't hit anything except all these other fields, and now they're just laying around out there. It's the background. It's the background. It's like the painting on the wall, and everything else is things. It's just everywhere. It's just everywhere. Okay, this is sort of horrifying. This is the central nuclear, and this is from 1955, and they're doing nuclear experiments. Lawrence Livermore, National Laboratory Destroyer of Earth. Watch this. This is horrifying. This is a nuclear explosion. Now I'm going to just stop it right there. And I've got it running on super slow, and it's already slow. You see the symmetry? You see this? What the hell is going on there? This is the explosion ball working its way towards zero. So as far as I'm concerned, it was a mid-air nuclear explosion. Look at this. This is just stunning. And of course, it's an extremely slow motion. And boom, it hits the Earth there. Now, to me, there's a symmetry in there, obviously, that has certain regions that are being separated for some reason. I mean, there's no way you can miss that. All right, this was after the first explosion showing it, but here it comes again. And it's just, see it, the ripple coming down? And that's real. That's not just an accident. And now, boom, you see it? Something else is going on here. But these are so symmetrical that there's no way that's an accident. Absolutely impossible for that to be an accident. Now, it hits the Earth and creates this. And watch what happens with these. They sort of mushroom back. And then everything hits the Earth, and it's a bad day for that particular region. Look at that. Now I have this running on spectacularly slow speed. And now it's just total devastation. It's going to go on for a while here. You see it, and by the time it gets way out here is where we're actually getting impacted by the black particles. All right, the original one back here, when it first hits, all the white particles come first. All right, so let me get way back here where it first hits. Boom. It's just nothing but whiteness. All right, just nothing but whiteness. And then as we get out a little further, the whiteness starts to dissipate, and it's getting dissipated, and now we're starting to see the black particles pushing the sand and all that. There's still a bunch of white in there with it, but this is the particles that actually do the damage. When I say do the damage, they push other things. The white particles don't push anything. They just burn things. And I mean, they really burn them. All right, I either showed you or will show you the mid-air explosion, but here is what happens at the ground to buildings and so forth. Now, there was a truck here. They moved the truck. I have, oh, what happened to the truck? This is all a big lie. It's amazing what people will come up with. The truck was here. They delivered all this stuff and set it up. They moved that truck. They have a hardened enclosure that's not going to get knocked down by anything. It's extremely hardened enclosure facing this way so that it can watch these events happen. So that is the setup. So don't tell me, oh, this is impossible, this is ridiculous. It's incredible what people will fight against now. Conspiracy people. This truck got moved, and then they set off the atomic bomb. And watch in these, this is to see what's going to happen to the structure. Everything's going to burn up. It's just going to burn and not even move. And then the black stuff will come and knock it down. So that's the two events. The first event will be the white just burning everything. The next will be the explosion. So here it goes. They're moving the truck. The truck is not there anymore. All right, now look, you see it burning? Burn, 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 burn. It's just smoking. Nothing's going anywhere. It's just like vaporizing. You see that? This is atomic vapor. Light, the energy part of light, is atomic vapor. I didn't know when I first wrote my paper about, well, I showed it a million times, about light is atomic vapor, and it is. But this was what I was thinking of as atomic vapor. But it also, the black part, is part of light as well. I didn't know when I wrote my paper long ago. I only realized it after working with Rod, seeing the actual pictures. So what we have now is the white is hitting here. Just look at the wires are smoking. All right, whatever that fed is going to burn. Remember I said particles hitting wires and so forth, that's coming down to cosmic, the coronal mass ejections. That's what they worry about, frying the circuits and interrupting with all kinds of communications. Yes, because they're hitting whatever wires communicate and whatever wires send electricity, and they can infuse electricity into that wire just the same way they do in a generator. The same thing. They generate huge fields, and it's got to go somewhere, and it would go into whatever these very, very tiny devices we have now and explode the chips. So here it goes again. Let me just go back. I don't want you to miss anything here. All right, again, the truck is going to be moved. All right, so they take the truck out of here. They set off the atomic bomb, and I'm going to stop it. Boom, I stopped it. What do you see? Nothing but white. Still, nothing is moving. That's just, and I can't account for it. I really can't account for how that energy is so extreme with no mass to speak of. How, can you figure it out? I can't. How can it have this much energy but no mass? No mass. Watch what happens. There's just no mass. There's nothing's moving. It's just glowing like crazy. because that's the first part of the atomic bomb to hit, is the white. All right, so here it goes, and it just smokes. Its white particles are invading the normal whiteness of matter. And it's just smoking, but they're not going anywhere. And it vaporizes everything. Look, it's just like it was boiling off of there. There's nothing. And now watch, boom, that's the black. Now watch, it'll turn around and come back, because there's a void back here, because everything's been gone out, and now it all has to come back. That's an atomic bomb. Okay, well, this is what you have to understand. Electron flood theory is completely different than this. They say the atomic number or nuclear charge number is the charge number of an atomic nucleus. All right, it says in a neutral atom, the same protons is the same number as electrons. So they're showing protons in here, these pluses are the same as electrons. Well, in reality, protons are not big like this. They're all dipoles. And so are the neutrons. So it's just a big ball of particles in the center. It's not protons and neutrons. You see what they say here? This is all plutonium. These are all plutoniums. And they say there's 94 protons, and then they throw in all these neutrons. Neutrons are nothing but protons with one extra electron attached. So really it's just a bigger and bigger ball of dipoles. So this is what we need a whole new change to here. So here's what happens in a nuclear reaction. You get plutonium, all right, and the plutonium has a whole series of isotopes. Isotopes means you have either not enough particles, all right, to reach stability, and plutonium, whoops, there goes my dark matter. Plutonium never gets to stability that I can see. Usually there's a stable state somewhere in here, and I see nothing that says stable, so I'm not going to dig too deep into this, but I don't really care. These are all plutoniums. We say, well, how could that be? How could plutonium be everywhere? It's all it's doing is adding one or two more of these little particles at a time. So here's the weight. Isotopic weight, mass, is the weight. Okay, this is the weight. 228, 229, 230, 231, 232, 233, 34, 35. They're just adding another particle. 36, 37, and then they get into some kind of other stuff. And then these are voltages and energy levels. I really don't understand that, I got to be honest with you. But it's the weight just keeps getting bigger and bigger. So now what happens way up here? A semi-stable plutonium in the most stable range would be this big, let's say. And it's not going to fall apart real easy, but you can break it up semi-easy. But then if you added all this extra stuff to it, that just doesn't want to stay together. That just wants to explode. When they're way below, way down here, they want to take on more particles. They're down here, and they're saying, I can't exist in this energy level. I'm going to decay, and my half-life is going to be like a bazillionth of a second. And the decay mode means either you're going to go up or down. And in this case, the daughter isotopes are uranium and neptunium. All right, from plutonium, they drop to these isotopes. Well, what does that mean? You had to give off a bunch of energy, because these are smaller. All right, you got plutonium, and you got neptunium and uranium. So these are the daughter isotopes. So from here down to here, you lose a whole lot of mass. Well, what does that mass turn into? It turns into electrons, and the electrons turn into light, and the light turns into burning rays, which we saw in the atomic bomb blast. That's why these give off huge amounts of radiation, because they just got so many extra particles attached to them. Now, they do something to them. They refine it. I don't want to get too deep into that because it really is kind of scary. But they refine it so that there's a certain product of isotopes that are extremely unstable. Extremely unstable. And then all they have to do is get a little boop, and then they just go off. All you have to do is compress it and everything goes. At that point, it's just all games are off. And these are all the different daughter isotopes. And I'm not sure which, I don't want to get too deep into that. It doesn't matter. But this is isotopes of everything. Now, you can't account for these isotopes with a standard model, because plutonium is supposed to be only so many protons and so many neutrons, and that's it. Well, no. Well, how did all get all these different states of plutonium? It's all throwing an extra neutron, throwing an extra neutron, throwing an extra neutron. No. They just got more and more dipoles, or less and less. It depends on which side of the isotope you're on. There's a stability zone normally, and then this side doesn't have enough electrons, and the other side has too many. This one wants to give some off, this one wants to take some on, and they want to move into the stable zone. That's all you got to remember. All right, I showed you the isotopes of plutonium. Every single one of these has isotopes because there's a bazillion particles in between each one of these. Because the protons and neutrons are made up of either 1823 or 1824 particles, not just a couple of quarks. So they have tons and tons and tons of isotopes. Well, they decay. Decay can create energy in the form of radiation. Yes, it's decaying. It's giving off a bunch of extra radiation. Process is called radioactive decay. It occurs when the nucleus of an atom is unstable, yes, and emits energy in the form of dipole electrons. The energy is released in the form of ionizing radiation. Ions are particles. They're talking about ions, but they're not only ions. They're also the dark part that goes with that ion. It's actually an electron, I believe. I don't think they have just absorbed extra electrons, because you can't. The dark part is going to have more pull to the white. So it's the core that really makes how tight the electrons are held. But anyway, that's a whole other story. So, but the energy is released in the form of ions, which can include alpha particles, beta particles, and gamma particles, which is the gamma is, so they're saying, yes, exactly what I just said, because gamma up here has no more white particles left. This is just the black particles. All right, by the time it spins so fast, at this point, there's a place in the ultraviolet, which is called the ultraviolet catastrophe. And you can go hotter and hotter and hotter and hotter. All of a sudden, it drops down to zero. And then all you got is the black. The black has no heat. So the temperature goes up and up and up and up and up, and then you hit these high energy rays, and zip, it drops down to zero. No more energy. Most people have no clue about that. I think I might have been a little out of focus, but these are the different frequencies. When you hit a certain frequency in an ultraviolet, it goes to what's called the ultraviolet catastrophe, which means it goes hotter and hotter and hotter and hotter and hotter, and it just drops right down to zero. And that's because there's no more white particles left. It's going too fast for the white particles to be along with these heavy particles, the black ones. All right, this is one of those rabbit holes. I'm in one of these moods today. I'm just going to continue going. I just talked about the ultraviolet catastrophe. I explained at a certain place just past the visible spectrum in the ultraviolet, it just drops right down to nothing. No more. Anyway, let me just show you here. This is solving the ultraviolet catastrophe. No one accepted Max Planck's explanation. And there is no explanation for assuming energy corresponding to particular wavelength quantized rather than continuous. They said it should have just keep going, 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 but it doesn't. And here's the evidence right here. The wavelength of radiation in nanometers. Okay, so the wavelengths is kind of long here. We're coming up here. And then it gets up here and gets up into the visible spectrum. You see it? Zip, coming way up here into the visible spectrum. Once you hit 5,000 K, that's as high as you're going to get into the visible spectrum. And then it just drops right off. That's the ultraviolet catastrophe. No more radiation. Well, radiation is heat, is energy. It's basically light. At this point, you don't even have any light left, I don't think. I don't think they can show you light, because all it is gamma rays and X-rays. They're subatomic particles at this point. They're no longer light. That's ultraviolet catastrophe. Like I said, this is a rabbit hole I'm not going to jump out of. I'm talking about matter. And what is everything made out of? I'm saying is made out of biology. They're talking about nucleosynthetic fingerprint of the outermost protoplanetary disk and early solar system dynamics. Well, what does all that boil down to? It means what is all the matter made of that they can see. And it says knowledge of the nucleosynthetic isotopes. Remember I talked about isotopes? Of the outermost protoplanetary disk is critical to understanding the formation of early dynamic evolution of the solar system. This is the most important part right here. The nucleosynthetic iron, magnesium, silicon, chromium compositions of this material. That is the composition of life. Iron is basically all blood, and silicon is ubiquitous. Now, these nucleosynthetic particles, compositions of this material, reveal that contrary to current belief, the isotope, again isotope signature, of the comet-forming region is ubiquitous. It means it's everywhere among outer solar system bodies. It's everywhere in the universe, possibly reflecting an important planetary building block in the outer solar system. It's everywhere. It's not just in our solar system, it's in the entire galaxy. This is why we need a new atomic model, and we need to understand dipole electron flood theory. And here it is right here, very simple. Dipole electron flood theory. It's up on the internet. Dipoleelectronflood.com. This is it. And these are the only two particles that exist, the black one and the white one. And when they glue together, they make a gluon. Two gluons back to back form a proton, a photon. That's all there is. And then the next stable, and these are pretty stable, the next zone of stability is going to be about 1823 of these particles together in what they would call a proton. And they seem to be stable at these different periods. That's why they call it periodic table. This weighs so much, this weighs more, this more. And all it is bigger and bigger and bigger balls of dipoles, as far as I can determine. Now, we need to look at this closely, obviously, but I think I've presented enough evidence to support my statements. And it changes chemistry, it changes space, redshift goes away. You know, the cosmic radio background, even the global warming is affected by understanding dipole electron flood theory. And I think I've made it pretty clear. Now, I expect to be peer reviewed and said, maybe this changes things. Maybe it does. If it's right, it changes things. That's no question whatsoever. But if it's not peer reviewed, who the hell ever knows?